Okay, so this completes the EM algorithm. So now what we will do now is we will see how to implement this EM algorithm for the case of the mixture densities that we saw. Okay, that is what we will see now. Let us look at that. Now EM algorithm for GMMs. I will write down the equations, okay, and skip the algebra. Take algebra as an exercise and please do it. So I will formulate all the distributions. M step is what I will leave as an exercise, that argmax. You'll have to just differentiate that function and find out what the next iteration is. We'll stop at that. Okay. So let us look at this. So for a GMM, first of all, P theta of x is what we need. Okay. Now recall that for a latent variable model, P theta of x is given as the marginal over the joint distribution between x and z, correct? Okay. Now in a GMM, how do you write this? You have this z, okay. What is a GMM? It is some alpha j times normal distribution, right? And we have mu j's and sigma j's, correct? This is what a GMM is. This is over j, okay. Now this can be looked into as a joint distribution. Why? So what is actually happening here is you can write this as P theta of z times P theta of x given z. This is writing the joint distribution as product of conditional and marginals, right? Now can you see the similarity between the second step and the third step? Okay, we can model P theta of z to be, or rather z to be, a discrete distribution, okay, with parameters alpha 1, alpha 2 up to alpha m. So remember we just saw a discrete distribution, right? So z is a discrete random variable in this particular case which can take values 1 to m with probabilities alpha 1 through alpha m. So somebody asked me a question 2 classes before, right? Why should we take this alpha to be bounded between 0 and 1? It's because of this. So these are probabilities. We are looking at discrete random variables and these are probabilities of taking this particular mixture. So z is this. And what about this random variable x given z? X given z is a univariate Gaussian, okay, with mean. So z equal to particular j, so mu is equal to, or you take mu j and sigma j. Right. Now therefore this expression now, okay, is exactly this. So P theta of zj is alpha j and P theta of x given z is a Gaussian. Is it all right? Okay, this is the joint distribution. Now actually, right, I mean GMM can also be used as a sampler. It's a generative model. I will not talk about it yet, I'll talk about this at the end of the course when we look at the generative models, and I'll revisit GMM later in the course. But I'll just give you the intuition. So what's happening is like this. A Gaussian mixture model can be looked into as you first toss a coin, or not toss a coin, I mean here roll a die, roll an M-faced die. Now depending upon what face it turns out to be, you pick that particular Gaussian and then sample your X. That's what GMM is doing. So if there were nature generating data, okay, you assume that your data is generated. When you assume that your data is generated according to a GMM, what is actually happening is this. Nature first rolls a die, an M-faced die with probabilities alpha 1 through alpha j. Then some face comes up. Conditioned on that particular thing, you sample from the mth Gaussian, that's it. There are m such Gaussians. That's exactly what's happening here. See, any latent variable model can be interpreted that way. So first you sample from P theta of z, then you sample from p theta of x given z, that is it. That is what is happening. See, any joint distribution is that way, no, you first sample from one of the distributions and then condition on that particular distribution and sample from the other, that is what is happening. Okay. So this is p theta of x, p theta of x and z, and this is your p theta of x, is that all right? Okay. Now let us work out EM for this. So what is theta here for this particular thing? Theta is that we have alpha, set of alphas from, okay, let me write that, alpha 1, alpha 2 up to alpha m, and we have mu 1, mu 2 up to mu m, we have sigma 1, sigma 2 up to sigma m. These are the parameters that we want to estimate for this model. Alright. So alphas are scalars, okay, all mu's are in Rd and all sigmas are in, yeah, they are all matrices. Alright. So let us write down EM. So what should we do for EM? Initialize theta, right? Initialize theta, theta t. Okay, we already have theta t. Now what should we do? We will have to now first compute the variational distribution. Compute what? Q t plus 1. What is this equal to? Is equal to p theta of z given x, the posterior. What is at theta t, right? This is computed at theta t. What is this equal to? This is, let us use Bayes' law, times divided by the sum of this. Correct? Okay. Do we know all these distributions? What is p theta t x given z, x given z? That is a normal distribution, right, computed at, it is mu t j, correct, and this is times alpha right, and divided by that entire thing. Now you take that and sum it over, the same term over j. Is it all right? So can we compute this? We can compute this. So I will not do the algebra, you can compute this. You will get a closed form expression, please complete it, do it. Okay, but we can compute this algorithmically. Any questions on this? So we got our Q T Z.
So this will be computed for every j.
Which one?
The numerator.
Of course, absolutely correct. This should be computed for each j because this is a distribution over z. You don't have to do it for every z. See, this will become a function of j, that's it. See, z is a discrete random variable with m possible values. So this distribution will be a discrete distribution with m possible values. So this is the normalizing constant in the denominator. Whatever you have in the numerator will be a function of j, and that's why you have m values, that's it. It's a distribution. What you are computing here is a discrete distribution with m values. Is that clear? So when you do this, for every j you get a different value, of course, right? That's a distribution over j. All right. We know all of this, right? We know alpha jt, we know mu jt, sigma jt, and so on, because we know theta t. Everyone clear with me so far? Okay. Now what is the next step? So compute f theta of qt plus 1. This is the expectation step. What is this equal to? Expectation of log, no, this is p theta x and z divided by t plus 1, it is with respect to t plus 1. Okay, let us write this. What will happen to this? So this qt plus 1 is now, should I write it again? Okay, let me write it again. Expectation is with respect to the distribution, just being a little lazy, EM algorithm does not let me be lazy. Okay, let me write it down. So this qt plus 1 is what? Z given x, right? This is what it is. Correct? Yeah. So this is equal to, this is a distribution over z, so we have a sum over z, correct? This sum is over z. This is log of what is p theta x and z? P theta x and z is p theta x given z times p theta z divided by p theta t z given x, right? Now this is equal to log, what is p theta x given z? It's a Gaussian at, please note that there is no t here, okay, because we will differentiate this with respect to mu j, and when we put it to 0 we get mu j t plus 1. You see what I am saying? There is no t here, okay, and this is, what is the second term? Alpha j. See, if you can appreciate why there is no t here, then you have understood the EM. However, in the denominator there will be a t. What is p theta z given x? This entire thing that we have computed here, I cannot write it there, but we know what it is. Denom, I will write it as denom, and this denom this is what we have computed, and note that this denom is a function of t, sorry, I mean theta t, it is a function of theta t. Do you get it? Yeah.
That alpha j would be outside actually. Theta j is outside, right? It's not inside the log, right?
Which one?
Because we are taking expectation, so there would be probability term outside.
Inside the p theta t z given x log that thing, that will be something.
There will be an alpha term outside. Yeah, so there, yeah, I was going to write it. So there is a, what term is this? This is alpha j t, because the expectation is with respect to p theta t z given x. Yeah, there will be a, this entire thing is multiplied by alpha this is j equal to 1 to m. Just to lighten the mood, right, I will just tell you one. I was a student. This EM algorithm is general enough to be applied to any latent variable model I told you, right. there are another class of models which are not used very seldom, which are not used very often these days, are what are known as hidden Markovian models. And hidden Markovian models with Gaussian mixture model transition probabilities, meaning there, imagine that there is another level of stochasticity that is on top of it, okay, which means that there will be 20 other notations and you will have to work out EM for that, okay. Now I had a book, my notes where I used to write all this, and after this class I wrote, I mean I still have that book with me. In the first page of that book I wrote, beware notationally hazardous. So you run out of alphabets, right, when you are doing some of these statistical stuff. Anyway, so you understood why there is an alpha tj here, right. Now what should we do? So what is this LHS? The LHS is f theta evaluated with qt plus 1. Now the part that I will leave to you as an exercise is, that's actually easy, easy meaning algebraically easy. You will have to do that. You will have to find mu t plus 1, okay, j as will you please do this? I want you to complete the algebra. So what is to be done is that you will have to differentiate this entire thing with respect to mu j. So this thing now will become a function of a mu jt, sigma jt, alpha jt and so on, which you have access to, and you do the same thing for sigma, you do the same thing for alphas.
So how do we have access?
Hold on, it will also be a function of x, because there is an x here, no? Because remember that we started everything with data, and also remember that we are doing all this for a single data point, and whatever estimate that we get, we will have to put a sigma I equal to 1. So this, what will happen is, this will be xi in that case. We are doing it for the ith data point, we do it for all n data points. We will have to just put a summation over all n data points after we get this. This is for a single data point. Now you understand why I did it for a single data point. Otherwise there should be another summation outside it and so on. So we are maximizing the likelihood. So will you do this? It will be a very nice, it will come out. When you differentiate this and put it to 0, the mu j t plus 1 term will simply come out to be a function of mu jt, sigma jt, alpha jt. Not only one j, it will come as a function of all of them, because denominator has a sum over all of them, you see. And it will also be a function of x, of course, because we are data that we are looking at. Okay. So this completes the EM algorithm for finding the parameters of a GMM. Okay, any questions on, please complete the algebra, because if I do the algebra it will take me 90 more minutes. You just have to write down, differentiate, it's 12th class calculus, please do it. It's not complicated at all, do it. Any questions on this? See this EM algorithm, 5 more minutes. This EM algorithm is general enough in the sense that you can apply it for any latent variable model. The only requirement is that if you want to apply it, you will have to have access to the correct variational distribution, which is the posterior of z given x. So why was this possible in this particular case? See, just notice this. I don't know if you notice this or not. In the case of a mixture density, not only Gaussian mixture model, any mixture density, we have access to the posterior because we can use Bayes theorem and write down the posterior in terms of the conditional distributions and the prior, right, or the marginal, and this we know because any mixture density, this is the probability with which you select a particular mixture. So you can look into a mixture density as a two-step process. You first select a particular mixture, a component, and then you sample from that particular component. Suppose you have m Gaussian densities that you are dealing with. What you are actually doing is first sampling from a discrete distribution to select which density that I have to sample from. Please note that this first level of sampling is to select which of the Gaussians to sample from. The second level of sampling is actually sampling from your data space, which is RD. The first sampling is in the discrete space. See, I will give you a concrete example. Let us say that we are modeling the images of X-ray that we have using GMMs. Do you still remember those X-rays? Or we come too far? We are not, actually you should not come too far, I mean you should remember the entire thread, okay. Now you remember what are we doing? We are trying to model the underlying distribution for that as a GMM. Now the first sampling that we do, which is rolling the die, the M phase die, is telling me which Gaussian to choose from. So there are M Gaussians here with their own mean and their own variances. Now the first level of sampling will tell me that okay, choose from the fifth Gaussian. Now I have to sample from that fifth Gaussian density. When I sample from the fifth Gaussian density, I get a vector of RD, right, because I am talking about Gaussians in RD. So I get a vector in RD and that is my image. We are assuming that the nature has given us images this way, that it first throws a die, M phase die, and then it selects which Gaussian to sample from, and it samples from one of the Gaussians, and that is what we have as data. So now you can see why this is a generative model as well, because suppose we are given some data, we run EM and get a GMM. Still remember that we are trying to minimize the KL divergence between this is our P theta and we have our Px. If we have done this well, then we have gone close to the underlying actual distribution, which means that I can actually generate data now with this. How? I know how to roll a die, and then I know how to sample from I am assuming that you people know how to sample from a Gaussian distribution. Do you? Do you know how to sample from a uniform distribution? The biggest irony of the world, right? You create a deterministic algorithm to sample from a random distribution. That's a random number generator. You have pseudo random number generators, right? They are deterministic algorithms to sample from a probability distribution. Ironic. Anyway, so if we know how to sample from uniform distribution, we also know how to sample from Gaussian distributions. How? There are these deterministic transformations that take from uniform distribution to Gaussian distributions, right? That Cauchy transformation that is there. So now if we know how to sample from Gaussian distribution, then we already have our first generative model here. If you are given data, this will be part of your assignment, by the way. Given data, run EM and then sample from a discrete distribution, and then conditioned on that discrete distribution, sample from that Gaussian distribution with the given mean and variance that you have gotten from running EM, and that should look like the image that you have in your data. Okay, so that's why GMM is also a generative model, because implicitly it will allow you to sample. Now in our case, we are using this to estimate our class conditional densities, because remember our goal was to design a base classifier. Okay, so yeah, questions on this? No, not choosing, the sampling from GMM. Yeah.
Before that, we were first choosing which Gaussian to pick, and then we
That is sampling from GMM.
actually we get the probability distribution of the image and not the image.
No. See, that's what I am saying. It will tell you which Gaussian to sample from, and if you know how to sample from a Gaussian, you get a data point which is an image. So that is why I asked you, do you know how to sample from a Gaussian distribution? Suppose I give you a mean and variance of a Gaussian distribution. Do you know how to sample from it? That's why I asked you. Actually we do, because if we can sample from a uniform distribution, then we can sample from a Gaussian distribution as well.
We start out with finding the distributions from
I agree. I mean, this was an off tour, a detour where I told you that GMM can also be used for sampling as a generative model, but yeah.
If you sample it, then you kind of generated
Sampling is generation.
right? Then
To me, generation is sampling and sampling is generation. That's it. Remember our initial discussions on guys, hello. Remember our initial discussions on sample space and random experiments and so on, right? What are generative models? Generative models are the ones that will carry out that random experiment, and we have the entire machinery to take care of, right? I mean, we have this random variable as a function. Finally, what you get is an element from the range space of this random variable function by conducting that random experiment. That's a generative model. All generative models are samplers. They are actually samplers. Okay. Again, as I said, there is an entire course on generative modeling the next semester that I will be teaching. So yeah, so GMM is the most primitive generative model that one can think of. Yeah. Good question. There are certain models, okay, where Z is taken to be continuous, but at least for the mixture densities, Z is taken to be discrete. But nothing stops, the math does not stop you from considering Z to be a continuous random variable.
In the last line for EMF or GM, we are taking the expectation with respect to the P theta of Z by X. Right? So where are we writing alpha J? Shouldn't it be P theta T of Z is equal to J by J
Oh,
given X?
Dick should be, I think that's actually the correct observation, because the expectation is with respect to,
QT.
yeah, so this should be thanks for that. This is what you are saying, right? This is correct. Yeah. Yeah. Note this correction. Okay. So this had to be p theta, but we know this, right? This is our qt plus 1 that we have computed theta t. We know how to do this. Yes. Thanks for noting that down. Okay. So next class, what we will do is we will look at the maximum a posteriori probability estimates or map estimates, which is a Bayesian way of estimating the densities. See, so far we have assumed the entire dependency that we have right now, okay, is on data, meaning we are minimizing the KL divergence between p theta and px, okay, and we are estimating only by looking at data, but data can lie. Example, suppose you are estimating the probability, the parameter probability of success of a Bernoulli random variable, which is a coin toss. We saw what is the estimate, right? The estimate is count the number of times it is favorable for the particular thing and divide by the number of events, right? Number of iterations. We just saw that, right? We did it for a discrete, generalized discrete random variable. Now suppose you are tossing a coin, okay? You toss it 5 times, you have 5 data points. And it's a fair coin and all of them can turn out to be heads. Possible. Now what is your ML estimate for that parameter P? That will be 1. That's a very bad estimate. You have just gotten unlucky, right? So the moral of the story is relying only on data is a bad idea, especially when you have less amount of data. So what do? So you have to have other mechanisms where you incorporate your belief about the system that you have into the estimation paradigm. For instance, in this example that I just cited, suppose I know that I am dealing with a biased coin. I know for a fact that probability of head cannot be 1. But my data ML estimate is telling me that this probability is 1. So I know that it's a bad estimate. Now can I incorporate my belief that I know, that I have, into my estimation paradigm is the question. It turns out that you can, right? How do you do that? By assuming a distribution over the parameter space itself. So far we have assumed our parameter theta to be a deterministic variable, right? Now you say that with certain probability my parameters can take value. So in mathematical sense I am assuming a distribution over theta, which is my prior belief that I have. So I already know that with certain probability my theta can take these values. whatever I am estimating can take certain values with certain probabilities is what I know already. So how do you incorporate that into your estimating paradigm is the question that we will be asking next. And these methods are called Bayesian methods for parameter estimation, out of which we look at one particular method which is called the MAP estimate, maximum a posteriori probability estimates, and then we will move on to non-parametric densities. Okay, so that's it. That brings us to the end of this class. Thank you for attending.